Welcome to my classroom. This is Justin. Today I'm going to talk about t-test and how it is different from z-test. So we'll start with z-value and z-test and how the concept of t-test can be explained from the z-test. So we all are aware about the z-value. So the z-value is a standard score. So to do this test, you should be aware about the concept of standard score, the level of significance, and the area under normal curve. Now, z-value. So what is z-value? Z-value is something like how much data is deviated from the center in terms of standard deviation. That is, what if your mean is 30 and your value, a particular sample mean is 30 and you have a score of 40, okay, and now how much this mean value and the score that you have x, how much score is deviated from the mean, that is 10, right? 10 deviation from value to the mean. Okay, now the z value is how much this deviation is in terms of standard deviation. For example, the standard deviation, let us say, is z value is the standard deviation value is 5. Now this 10 divided by 5, that is 2. Now I would say the value 40 is deviated from the value 30 in 2 standard deviation level. Now this is the way. So one way of explaining the deviation is based on how much exact deviation exists. In terms of standard score, the way we explain the deviation from the center is in terms of standard deviation. So 2 standard deviation away from the mean. See that? Like this. Now this is called a z value. So if you remember the equation of the z value is something like the value x minus the value mean, let us say m value divided by standard deviation. So this is the z value. So once again, the standard score z value tells us like how much the particular value is deviating from the mean in terms of standard deviation. So this is z value. Now what's the application of this z value in the inferential statistics? So let us say we have a population. So this is my population. Okay, so population. From the population I take a huge number of sample and that sample mean, if you take, that will follow a distribution, let us say like this. Okay, now if I take a sample from the population, that will have a mean, and if I take another sample from the population, I will have a small difference in that mean. Like that, you get different kind of mean. So that values, if I plot, I'll get a distribution like this. This is called a sampling distribution. See this? This is a sampling distribution. That means distribution of all possible samples with a specific sample size. Now, what would be the mean of this particular sampling distribution? Let us say this particular value called as mu. Okay, statistically we generally call as mu, and this will be generally same as this population mean itself. That's the average of all samples. If you take consider another average, you will get the same value as. So that means population mean would be same as a sampling distribution mean generally. Now the application is, what if I have a value of assume that the population mean is around 85. Let us say 80, okay, and I have a sample here, a sample of, and this mean is 100. Okay, generally we do not know the population and assume that you know the population value. Okay, the average population mean and the sampling distribution mean, that you are aware about that, and you have a sample, let us say, of 9 members. Okay, and standard deviation of that, this 9 members score is let us say 6. Okay, so standard deviation of the sample is 6. The sample has 9 members and the average is 100. So this is a condition. So I have a value like this. So my question is whether this how much this 100 is deviated from the 80. See that? This is mean, this is the value that I have. If I use this equation, z value equation, I have x value that is 100, I have mean value that is 80, and I have standard deviation value. Do I have a standard deviation value? No, I don't have a standard deviation value of a distribution. So what do? You cannot really calculate a standard deviation value of a distribution like this. The standard deviation value of the population is not same of the standard deviation value of the distribution. So based on the central limit theorem, we have an assumption that the standard deviation of the distribution, okay, I call it a standard deviation of the x, something like that, the standard deviation of the distribution. So the x has nothing to do with the distribution, I'm just calling this like this, okay. The standard deviation of the distribution is basically standard deviation of the population divided by n, square of it. So this particular concept is standard deviation of the distribution is same as standard deviation of the population. I'm just writing as p here, standard deviation of the population, square of it, and divide by n. This can be written as standard deviation divided by root n. So this is the standard deviation of the sampling distribution. Okay, now so I have all these values here in this context. Now the next question comes, what is the standard deviation of the population? I may not be knowing that. Standard deviation of the population. So how do you work with this if you do not know the standard deviation of population? So here is the second assumption. What we do is you have a sample and you assume that this sample is representing the population. So standard deviation of the sample should be same as the standard deviation of the population if it is representing properly. Now I would replace this z value, the standard deviation value of the population by the standard deviation of the sample. Okay. Now because that's the only thing I know. So what I do is the standard deviation of the distribution is same as root of standard deviation of the sample square divided by n. That is the standard deviation of the sample divided by root n. Now the x value is, so the x value, the z value, the z value is x minus, this is 100, that is x minus the mean value, that is the mu value, divided by the standard deviation of the particular distribution, that is s, divided by root n. So this is a way we calculate z value. Now fine, this is very simple. So it's something like 100, I can write like equal to 100 minus the values 80 divided by standard deviation of that is 6 divided by root of 9. So this will be 20 divided by 6 by 3, that is 2. So together it will 20 divided by 2, that is 10. So what would I conclude here? The value 100 is 10 deviation away from the average value 80. See that? So I'll get how much the value, the existing value of the sample is deviated from the population mean. That's what I'm going to do. So what's the benefit of knowing this? I can understand what's the chance to get a value like this. So just assume this value is 0.001. This means that chance to get a value of 100, okay, or more extreme value, okay, assuming that this sample is taken from this population is the chance for that getting is this much, that level of significance, that is 0.001 into 100. That means 0.1% chance to get a value of 100 if we take a sample from this population. Generally I would say that there's a very less chance to get a value like that. So my assumption would be this sample may not be from the same population, it could be from some other population. So I would say that these two values are significantly different. So that's a concept of z test, and z test and t test is same. So what's the difference between that? Now look at this particular equation, z value equal to the x value minus mean value divided by this x is the mean of the sample, okay, the mean of the population. Now standard deviation of the sample and number of the sample in this context. Now the problem is this Z would be following a normal curve like this when this particular n value is greater than 30. If n is not greater than 30, this Z value will not follow a normal distribution. Now that's a twist now. So if n is smaller than 30, that means what if n is smaller than 30? Now this equation, this value, that statistic that I get from mean minus population mean divided by the sample standard deviation divided by root n, this statistic will follow another distribution called as t distribution. This is not a normal distribution pattern. The Z value is a normal distribution. T is not a normal distribution. So what's the difference between this normal distribution, Z distribution, and a T distribution? So T distribution is more like a leptokurtic curve. What is a leptokurtic curve? Where this area, the area here would be a little more go like this. This is a leptokurtic curve. So if this line is a Z line, this particular line indicates a leptokurtic T distribution. That means you have flat, little more thick areas here. You have more thick areas here. Okay. Now the end will be more like this. In other ways, I can say that standard deviation scores will be more higher when sample size is smaller. So data are more deviated like that. So you'll get a T distribution in this context compared to the Z value. So now the value is T distribution. So what's the difference here? The value that you get here, this point, if in T distribution, in the Z distribution it was 0.001, and that value won't be same in the T distribution. It will be a little more extreme, a little more bigger, not extreme, little more bigger. The T value will be a little more bigger like that. So there is a small difference in the T score and Z score. T score and Z score would be same, but the significance level would be different. That means area under curve will be different. So this is a T test, and that means when sample size is smaller than lesser than 30, the curve, that is statistic that you get from this particular equation will be following a T distribution. If it is more than 30, it will be following a Z distribution. So test, you can make the judgment based on the area under normal curve or area under curve. Okay, now this condition we call as a T test, this condition we call as a Z test. So if sample size is smaller, go for a T test. If your sample size is higher, it will follow a normal curve, it's a Z test. Okay, so when sample size is higher, see that equation is same in both contexts. So automatically the judgment also will be same, because when sample size is higher, this T distribution will become almost same as Z distribution. See that? So this is why most of the softwares you won't find Z test and T test separately, because it follows same kind of pattern. So what are the different types of T test? You have basically three types of T test. One is one sample T test. Okay, one sample T test is the same as this condition. Actually, what if, for example, consider a context where you have a sample and you need to know whether the sample is different from the population. That means you have just one sample, and to compare this particular sample to sample mean with some other value. For example, let us say I have around few kids with me whose social maturity score is, let us say 30. Okay, and this is sample, and I know that the social maturity score of students from third standard is 35. This is the population. In general, third standard students social maturity score is 35. Now my question is whether this sample belong to this population. is the difference between 35 as a value and the 30 as a sample, is it significantly different? Now this is a one sample t-test. That means you have one sample and you have a value to compare. That value theoretically we call it as, it's a population mean. So that's a conceptual kind of understanding. So it's a one sample t-test. So how do you write the hypothesis for that? Let us say sample mean, I'm just using sample mean, mu is equal to 30 or not equal to 30, like that. You can write the null hypothesis and alternative hypothesis. And second one is independent sample. Writing here itself. So you have one sample t-test and you have independent sample t-test. So what is independent sample t-test? Instead of one population mean and a sample mean, you have two different groups. Let us say I have group of males and group of females, and I need to compare whether the average score of them are equal or significantly different. This is called as a independent sample t-test. Why it is independent? Group of male is significantly different from group of female. Now they are independent. For example, the first person score of male is 35. Doesn't mean that the female counterpart, that means first person in the female group, get any score which is related to the score of the person in the first group. So that means they're independent groups. Scores of one group will not influence the scores of second group. That's the independent groups. Now the third one is paired sample t-test. The paired sample t-test is a condition where the group one, you have two groups to compare. So first group members would be same as second group members. So the sample are related, pair, connected. So let us say I have a pre-test and post-test condition. In this context, members in the pre-test are same as members of the post-test. So, or I want to understand the performance of the participants in the two conditions, like low noise condition and high noise condition. So the participants are same, their performance in the condition 1 and condition 2. So this is a paired sample t-test, or you call it as a related sample t-test. It is not necessary that respondents has to be the same all the time. For example, let us say I need to know the social maturity of students, which is evaluated by the parents and teachers. So both parent and teacher are evaluating same set of students. So parent of a student A will be evaluating the the child 1, and the parent, the teacher is also evaluating. So both of them, parent and teacher, has scores of same person. So my objective is to know whether evaluation of parents are same as evaluation of the teachers. That's also a paired sample t-test. So these are the three types of t-tests we have, and generally in general we can say that this is comparing two values, two groups, or two distributions, like that. So that's a concept of t-test and how it is different from z-test. That's it for today. Bye from my classroom.